Hey, pre-calculus friends, we are in section 6.4 and we are going to be talking about the amplitude and period of the sine and cosine function. So let's go ahead and get started with a little bit of notes and vocabulary. So here we are looking at the first term, which is amplitude. And the idea of amplitude, let's see if I can get my pen. The idea of amplitude is really just the relationship with the graph of the function to the actual grid. So in a way, we're thinking about the height, like the maximum height that the function can go from the midline. That's one way of thinking about it. And another way of thinking about it is really just the absolute value of the coefficient of the function. So if we have y is equal to a times some number a times the sine of theta, like we do here in this blue graph, that the graph will be 1. Notice that the maximum height of the blue graph is 1, even though I'm going to call it like the span or the range is 2. We go from -1 to +1. If we start at the midline, the height is 1, and that's going to be the maximum height. And so therefore that is the altitude, the absolute value of that a value. Similarly, we could see if we had 2 times the sine of theta, then 2 would be the maximum height. That would be the amplitude of the graph. The next thing we're going to talk about is the period. Even though we defined period before as like the time it takes for one complete cycle to go through in terms of the graph, getting from beginning to the end of that repeating part, what we realize here is that we can use our equation to figure out what the period is. So this little number here, the coefficient of the theta value. So if I had, my coefficient in the above ones were 1, but if I had some number here that I was multiplying the theta value by, I can consider that as a coefficient. And what I could do is to figure out the period, I would take 2 pi and divide k, whatever that coefficient is, into 2 pi, and that would be the period. So we'll be using that technique, and this only works for the sine and cosine functions. We'll be graphing other periodic functions, but specifically for those you can find the period in that way. And finally, the idea of frequency. If you know the period, right, then the frequency is the number of cycles per unit of time. So the frequency would be equal to the period is equal to 1 over the frequency, and therefore the frequency is equal to 1 over the period, and I should have just done it like that. It's just 1 over the period. All right, so with that, let's go ahead and get started with some of these examples. Looking at example 1, we're going to state the amplitude for the function y equals 4 times the cosine of theta. And clearly, we can see that that 4 is going to tip us off. The amplitude is equal to 4, the absolute value of 4, which is 4. So if this were -4, the amplitude is still +4. Again, it's giving us the maximum height from that middle line of that periodic function. Okay, so let's look at graph this thing. So if we had to graph it, there we go. Having a handy grid might be helpful. And so we're going to start off and just remember a little bit of the points that we talked about in the last section, which is that the cosine function starts at 1, has a full period by 2 pi. And so it's going to start off at 1. It's going to reach our maximum point here, minimum point here, and another maximum here. It's going to cross 0 here, and it's going to have that telltale sinusoidal curve vibe. So it's going to do something like this. And we'll do the same thing back here. Minimum value down here, maximum value at -2 pi. It's going to cross 0. And so we're going to continue this curve in that direction. And then so you all know, hopefully by now, that in order to deal with this coefficient, basically what we're doing is we're going to take each of these values and multiply it by 4. So 1 multiplied by 4 is 4. 0 multiplied by 4 is 0. -1 multiplied by 4 is going to be -1. So what you're going to see is that we're going to get a stretch. And of course, I can kind of go in here and do like 1/2 is going to be, and stretch those values. But the reality is it's going to maintain that curve with this stretch, this horizontal stretch. So vertical stretch rather, my bad. So I know this isn't the prettiest graph, but it's going to get the job done. All right, so trying to take my time to show the curve. There we go. All right, that's the best we're going to do right now. So that's our both of those cosine of 4 times the cosine of theta and just the cosine of theta graphed on the same pair of axes. And B says to compare the graph. And so what we're doing is comparing and contrasting. The shape is relatively the same. It still has the same period. Everything stays the same except the maximum and minimum height. Well, that's not true. Everything is multiplied by 4, and everything in terms of the x-intercept stays the same because those don't change given the fact that we're multiplying by 4. So that's the comparison that we wanted to talk about there. Let's see if we can get some more interesting problems going on here in example 2. So in example 2, we're going to state the period of the function. So here, this requires us to remember that we have a relationship. We know that if we can rewrite this as y is equal to k, or y is equal to cosine of k times theta, and in this case that would be the cosine of 1/2 theta. If we can look at this coefficient here of the of that theta, of that angle, the coefficient of the angle is going to give us the period, you remember? And that was just from our vocabulary notes above. So what we need to remember is that to find the period, we need to take 2 pi and divide it by k. And when we do that, or the coefficient of the angle, and when we do that, we see that the period of this function will be 4 pi, because when I divide by 1/2, it's like multiplying by the reciprocal, and so that's going to be 4 pi. All right. So for the second part, we're going to be graphing, and so they asked us to basically compare 2 graphs, which is to graph y equals the cosine of theta, which I have here in black, and now we're going to graph y equals cosine of theta divided by 2. And so basically, if y equals cosine of theta is this black line, y equals cosine of, I can kind of figure out the values using this line, using this curve here. So if when theta is 0, we know that the cosine of theta is 1. So if theta is 0 here divided by 2, we're still dealing with the cosine of 0, which is going to be 1. So we're going to get an intersection here. And so I'm going to kind of bounce through. So now what I'm wondering is, okay, well, what's happening at when theta is equal to pi over 2 for this function, for cosine of theta over 2. So when theta is equal to pi over 2, we're really, if I divide pi over 2 by 2, which we are required to do here, I get pi over 4. So what's happening is going to be the same as what's happening when cosine of theta is just pi over 4, meaning we're not going to get down that low. And if I continue doing that, so if I were to ask myself what's happening here, it's going to be the same thing that's happening here. What's happening when theta is equal to pi, for my green graph, it's going to be the same as when theta was equal to pi over 2 for my black graph. And so what you can see is this stretching, right, of the graph in a way. Let me see, this value would be here, and I would get my first little minimum wave here. So what would happen at 2 pi in the black graph is really going to, well, what would happen in 2 pi in the green graph is going to be what's happening in pi in the black graph. Hopefully that's making sense. So I get this. Let me try to draw it. I know you guys are giggling at how poorly this is coming out. When I have trouble, sometimes I just make it a little thicker. Let's try that. So we get this, you're not seeing the curve, but we get this really stretched out curve. And that, what we just saw, will continue on this side as well. So it's going to go up and then back down again, and then it would go up. So we've got a horizontal stretch. And you can see that the period is now 4 pi. You can see why it's 4 pi, because everything is taking longer to happen, and we would kind of continue on in that kind of way. Hopefully that makes sense. Let me know if you guys need help with that, because I know it's weird to graph online. All right, so let's go ahead and look at the next example. So here we're putting the whole shebang together. We are going to be graphing given a change in both the period and a change in the amplitude. So if we look at this, we know it's a sine function. We know what that looks like. So I oftentimes like to just have like a base sine function or a base cosine function graph, so I can then kind of work my way through what the graph would look like in terms of comparing. So I'm going to start off with that. Okay, so you can see here in red, I just pulled this off of Desmos. This is just a typical sine graph. And so now we can think about what's happening in reference to this guy here. So the amplitude, of course, for the function here in black is going to be 1/2. So we see that the amplitude of our function is 1. This is a 1 here, and this is a -1 here. I shouldn't call it our function, but the original function. So the amplitude of the function that we're about to graph is going to be right here. So it's not going to get any higher than a +1/2 or any lower than -1/2. All right, so that's what's happening. Ooh, that looks bad, but you guys with me? All right, so now we know 4 theta is going to give me information about what the period is. And so I know that the period is given as 2 pi divided by that k value, which is 4. So now I know that the period is going to happen, everything's going to happen for this function at 1/2 pi. At 1/2 pi, the whole thing is going to be done. So we're looking at a full cycle starting and ending here, and then a whole nother full cycle happening here all throughout. Are you guys with me? Hopefully that makes sense. So what does a full cycle mean? It means we are going to start at 0, and midway between there, we are going to get back down to 0. So we should have a graph that looks like this. All right, is that kind of making sense? The period is 1/2 pi. That side doesn't look that good, but you get where I'm going. You forgive me. Okay, that looks bad, but you see where we're going. It's this continuous function, this not just continuous, but this periodic function, and it goes in both directions infinitely, continues on to infinity. We see that what this 1/2 did is it truncated it, it made it shorter, but what this 4 did, this 4 being greater than 1, it actually increased the frequency of the cycle. It increased how quickly, or maybe increase the frequency is not what I want to say, decrease the frequency. All right, but you know what I mean. It made the period go much quicker. It went by much faster. So for this example, we're going to just be writing an equation, and we want a cosine function where the amplitude is 9.8 and the period is 6 pi. So let's get to the period first. We remember that the period was equal to 2 pi divided by k. And so in this case, what we need to do if we're looking for how we're going to write this equation, because we know the equation is going to be something like this: y is equal to blank times cosine of blank theta. And so we know that the k value is going to go here and the amplitude will go here, or some version of the amplitude will go there. And so we'll discuss that. So the hardest thing to do is this guy. So let's go ahead and figure out what k is. And we know that the period is equal to 2 pi over k, and we know that p, the period here, is 6 pi. So really this is relatively simple equation to work through and for us to figure out what k is. And with a little bit of work, taking the reciprocal of both sides, maybe if you like that, multiplying, figuring out, we get that k has to equal 1/3, because dividing by 1/3 is like multiplying by 3. So we know that the value here is going to be cosine of 1/3 theta. And what is the amplitude? It's going to be 9.8. So it makes sense to write 9.8. Similarly though, I have to be honest, we could have had -9.8. That would also satisfy this particular question. We haven't talked about what happens with the negative, but you guys know what happens when we throw a negative in front of a function. When we throw a negative in front of a function, we get a reflection in the x-axis, and that's something we will discuss a little bit later with these sinusoidal curves. Here in example 5, we're going to be referring to the application in the beginning of the text. And after we read through this, we're going to be finding an equation for the motion of the buoy. And then we're going to determine the height of the buoy at particular times at 8 seconds and 17 seconds. So here's what we have. We have a signal buoy between the coast of Hilton Head Island in South Carolina and Savannah, Georgia, bobs up and down in a minor squall. From the highest point to the lowest point, the buoy moves a distance of 3.5 feet. It moves from its highest point down to its lowest point and back to the highest points every 14 seconds. Find an equation of the motion for the buoy, assuming that it is It is at equilibrium at point t equals 0, so that's time 0, and the buoy is on its way down at the time. What is the height of the buoy? 8 seconds and at 17 seconds. So I'm going to try to draw a quick sketch of what this could look like. So we are told that at time t equals 0, and that will be where this axis is, we are at the equilibrium point and we're on our way down. So we know that we're going to go down and we're going to go back up again, and we're going to get back to an equilibrium point. And it said that whole thing happens in 14 seconds. So at 7 seconds, we should be at the equilibrium point. We get to our lowest point because it said we were on our way down. Then we come back up. This is going to be 14, and we're going to, kind of rock that move there. So what I'm thinking about is the sine function, right? Because we know the sine function starts here. And as we've discussed before, cosine and sine function are literally identical in most ways in terms of being able to express a situation in terms of either one. You can do it. But right now, the easiest one would be sine, since we're starting at the origin. And so we're looking at a period of 14 seconds. We're looking at an amplitude. That's going to be interesting. How high up do we go? It says here that the distance, the lowest point and the highest point, is 3.5 feet. So what that tells me is that the highest, if we're considering like a midline, the distance from bottom to top is 3.5 feet, and therefore we're going to be talking about 1.75 feet. It's kind of like the amplitude and the minimum. Does that kind of make sense? Because if I add 1.75, this part plus 1.75, I'm going to get 3.5. I'm hoping that makes sense. All right. So with that in mind, we're going to start off writing our equation. We know we're dealing with sine. So we have the sine here. 1.75 is the amplitude. I'm going to hold off on thinking about that for a second. And then finally, let's see if we can find what the coefficient of theta would be, right? So again, let me set it up like we did last time. It's kind of like blank sine of blank theta. And so we're just figuring out what that is. 1.75 is what I'll put here. And for the coefficient of theta of that angle, I'm going to use that relationship again. Remember, the period is equal to 2 pi divided by k. So I need to know what k is. And so I have period 14 is equal to 2 pi divided by k. Sorry, this gets all squingy and small. I'm going to scooch up a little bit. And so I'm going to solve for k, which shouldn't be too bad. Solving for k is going to give me, sometimes I'll do it this way. 14k is equal to, if I multiply both sides by k, 2 pi, divide both sides by 14, and I get that k is equal to pi over 7. So now I know that a pi over 7 goes right here. But if you were to graph this, we wouldn't get the graph that I just stated. We wouldn't get the graph that we are working on. And I'm sure you can guess why, especially from the last conversation we had. If we graph this, we're going to be getting this, like that. And that's not what we want. We want to get the opposite direction. And the way for us to do that is to throw a negative in front of this, because we're going down instead of up. So the actual equation is going to be written here in purple. Y is equal to negative 1.75 times the sine of pi over 7 theta. Hopefully you can see that all right. Okay, so that's how we would handle that. And we've got one more example. Here we are. We're going to write an equation of the sine function. So they're telling us the sine function that represents the initial behavior of the vibrations of the note G above middle C, having an amplitude of 0.15 and a frequency of 392 hertz. All right, so let's go ahead and get started with that. So let's look at this as y is equal to blank times the sine of blank theta. Well, they gave us the amplitude, which is really helpful in this case. Of course, we know that getting this value, we know that now that we could have a positive or negative value here for this 0.015 or 15 thousandths as it is there. But that's good enough for us right now. The next bit of information we need to deal with is the hertz. We know that K value needs to go here. K value is related to the period, and hertz is related to the period. Do you remember how the frequency is related to the period? Hopefully you do. The period is equal to 1 over the frequency. And so given that, we know that the period here is going to be equal to 1 over 392. So that's going to be the period. However, we need to find the K value. So now the period we know to be equal to 2 pi over the K value. But since we know the period, we can now calculate the K value. So with a little bit of work, 1 over 392, which is the period, is equal to 2 pi over K. And if I were to solve this, I'd get that K is equal to 2 times that value, which 2 pi times that value, which is going to be, I'm trying to do it in my head. Let me just write it down. 784 pi. So K is equal to 784 pi. So my equation could be either plus or minus 0.015 the sine of 784 pi theta. All right, and let's see, vibrations of note in the middle C. Okay, so that's what I'm going to go with. I'm going to leave the plus or minus. Maybe we can throw that off. I'm not quite sure. I think that's good enough though. I think it just depends on where the graph is, and maybe there's a picture of the graph in the textbook. Hold on, let's find that out. Well, this is the picture that they have in the text, and this looks like this would be better explained as a cosine function, so I don't know if they really meant this for anything, and this is assuming that this center line is the y-axis. So whatever, we can go with this. So basically there's two equations that we have. Either the positive or negative would describe the situation that they gave us up here. All right, with that, guys, we are done with this lesson, and I look forward to talking to you all soon. Let me know if there's any questions or concerns. Talk to you later. Bye-bye.